So my name is Henry. I'm a data scientist at Civis Analytics, and today I'm going to be talking about measuring model fairness. Before we get started, a quick outline of where we're headed. I'm going to start by motivating the problem a little bit. And here I don't mean just the problem of model fairness, but I mean the problem of why you should think carefully about how you go about measuring model fairness. It's actually kind of a slippery, tricky subject. So next, I'm going to talk about some different subtleties that show up when you set out to do this, when you set out to measure the fairness of a model's predictions, and give you some points to think about when you're doing this yourself, like different things to look out for and ways to think about this question. And then finally, I'm going to wrap things up with a case study that we did using some real-world data from some of our consulting engagements at Civis that shows how these subtleties can crop up when you're trying to measure the fairness of a model in a real-world setting with real-world data. So that's where we're headed. To start off with, I think there's a pretty broad consensus at this point that machine learning models can have a big impact on people's lives. So credit scoring models determine whether you can get a loan to buy a house. Advertising models determine what kind of job opportunities you get exposed to through job ads, or what kind of credit products or credit terms you get exposed to through credit offering advertisements. And machine learning models can even affect things like how long you spend in jail waiting for parole. So this is common knowledge now. People are pretty aware of the fact that these machine learning models have large impacts, and that's given rise to a similarly broad concern about how you go about making sure that these models are fair, making sure that these models aren't unfairly discriminating against people. Unfortunately, that's where the consensus ends, because figuring out how to answer this question of model fairness is slippery and contentious. And this example here about parole and models determining how long you spend in jail is actually very illustrative. So a quick show of hands, how many of you are familiar with the controversy around the compass recidivism model? People have heard of that? Handful? Okay. So the story here, for those of you who are unfamiliar, is that ProPublica, which is an independent investigative journalism outfit, did an investigation into this model called Compass that's used to predict recidivism, so predict the likelihood that people in prison will recommit crimes once they are released. So this is a model that is apparently used pretty widely across the country in informing decisions about parole. Like, this model spits out a likelihood that someone will go on to commit more crimes after they're released, and that score informs decisions about when people get released on parole. So ProPublica got some data about this model and about its predictions and analyzed it and came to the conclusion that this model was unfairly biased against black people. To support that conclusion, they looked at the ways in which the model failed. So looked at errors in the model's predictions. And what they found was that the failure rates were different for people of different races. So if you look at false positives, people who are labeled high risk but end up not reoffending, that error rate is about 24% for white defendants and about 45% for black defendants. Similarly, if you look at the false negatives, people who the model labeled as a low risk of recidivism, of having a low risk of recidivism, but that did actually go on to reoffend, that error rate is about 48% for white people and 28% for black people. So on the basis of this analysis, ProPublica wrote a report and said, this Compass model that is widely used across the country in making parole decisions is biased against black people. So that's one half of the story. After this report came out, Northpoint, which is the company that makes this Compass model and sells the product, responded by saying that the model was not unfair because it had similar overall performance for both white people and black people. And to prove that, they looked at the AUC. So this is a kind of a general measure of the quality of a classifier that tells you how much better it's doing than random. And they found that overall, this overall accuracy was the same, or very similar for white people and for black people. And similarly, if you just look at the total accuracy, like the number of predictions it got right over the total number of predictions it made, that number is also similar for both white defendants and black defendants. So on the basis of this, North Point said, no, our model actually is fair. So the question we're left with is, how do you decide which measure of fairness is appropriate? You might instinctively say, well, let's just make sure these are both satisfied. Like, make sure the errors are balanced and that also the overall accuracy is balanced. Unfortunately, in almost all cases, that is mathematically impossible. So once this controversy came out around the COMPAS model, some researchers went and showed that except in like very contrived cases, except in, for example, the case where you have totally perfect predictions across the board, then it's mathematically impossible to satisfy both of these decisions, both of these descriptions of fairness. So the question for us, and the question I'm going to talk about in the rest of the talk, is how should you think about how to define fairness in the context of the model that you're building or the problem that you're working on. And there are kind of a number of subtleties to this question. So next I'm going to walk through the 3 of these subtleties, 3 points for you to think about when you go to make this kind of classification model that might affect somebody's life. The first subtlety is that different groups can have different ground truth positive rates. So there can legitimately be differences between the rates of the positive class, like the number of ones your model spits out versus the number of zeros, between different groups. So an example I like to use here is, suppose you were building a classifier that was trying to predict diagnoses of breast cancer. According to these statistics, women get breast cancer about 2 orders of magnitude more frequently than men do. Something like 12% versus 0.1%. So there are very legitimate differences in the ground truth positive rates for this problem between genders. The issue is that certain fairness metrics make assumptions about the balance of ground truth positive rates. So there's one metric called disparate impact. This is also sometimes called statistical parity. And this metric assumes that the ground truth positive rates are balanced between the 2 classes, are equal between the 2 classes. The way this metric is defined is you just look at the probability of a positive classification for both groups and then take the ratio of that. But you can see how that implies that the ground truth positive rates would have to be the same for the 2 groups for this metric to be meaningful. In our breast cancer case, we're going to fail this test dramatically because there's 2 orders of magnitude difference between the classification rate. But still, this is a popular metric because it's the only one that is referenced in US case law. So there's a historical precedent for using this as a metric of fairness. So that's one subtlety. There are legitimate differences in ground truth positive rates. Another subtlety is that you don't actually know what the ground truth is. You only have data, and your data is a biased representation of what the ground truth is. Your data is not the truth. It's some biased approximation of the truth. There's a famous quote by the statistician George Box, who said that all models are wrong, but some models are useful. And I think in this context, you can adapt that to all data sets are biased, but some data sets are useful. So you can still use these data to fit models, but you have to think carefully about how your data is not reflective of the real world. There are a couple different types of bias that can show up in your data. And I think it's helpful to think about kind of the different types because that can inform how you think about measuring fairness. So one of these types of bias is what I call label bias. And this is when a protected attribute, so something like gender or race or age, affects the way labels are assigned within your data set. So I have here a quote from a paper that was investigating school discipline in I think like elementary school or middle school. And the authors found that students from African American and Latino families were more likely than students from white families to be suspended for the same types of problem behavior. So if you have a data set like this, and you set out to build a model that predicts like student will have problem behavior, but the label that you're using is student has been suspended, then you're operating with label bias because different groups are getting assigned labels differently within your model. And it's not an accurate reflection of actual student problem behavior. This is a problem because there are also several fairness metrics which are based on the agreement between your model's predictions and the labels in your training data. But if you're optimizing for agreement with labels, and those labels are themselves biased, all you're doing is perpetuating the bias that generated those labels in the first place. Here, a popular metric is called equal opportunity. And this is comparing, quote, true positive rates with your model's predictions. So looking at the probability that a given group will be classified as a 1, classified as a positive, given that their original training label was positive, and comparing that rate between groups. There's also a similar one called equal miss opportunity, which compares true negative rates. But here, again, the problem is this metric, this fairness thing that you're using to determine whether or not your model's predictions are fair, it's based on agreement with the labels. And if the labels themselves are biased, then you're not actually addressing the fairness question. Another way your data can be biased is if the sampling process that generated your data is different between groups. So the idea here is, you have some process out in the world which is generating the data that you're using to train your model. And if that process operates differently for different groups of people, then that's going to bias the data that you're using to train your model as well. The example I have here is a quote from an analysis out of Andrew Gelman's group of the stop and frisk policy from the New York Police Department. And in their analysis, they found that people of African and Hispanic descent were stopped more frequently than white people, even after controlling for geographic variation and estimates of crime participation. So if you're working with a data set based on like results from stop and frisk stops, then it's likely that that data set has sample bias because the process by which people are getting put into the data set operates differently for different groups of people. This is also a problem because some metrics compare ratios of classifications within groups. So I'm going to go back to disparate impact here. We talked about how this is the kind of the ratio of the positive classifications for two groups, but either the numerator or the denominator is kind of like the ratio within a particular group of different outcomes. So it's like the probability of a positive classification within a particular group. But if you're sampling groups differently, if you're sampling everyone in one particular group, but only high-risk individuals in another particular group, you're going to throw off that ratio and again compromise the utility of this particular metric when you're trying to assess fairness. So the last subtlety is that the consequences of your model matter. If you're making a model that is punitive, the consequences of your model's decisions are negative, you're handing out a punishment, then I could see making a case for caring more about false positives. You care about not punishing innocent people based on the output of your model. Similarly, if your model is assistive, like if it's handing out something good, handing out something positive, I could see you caring more about false negatives, not wasting your resources on people who don't need the benefit that you're handing out. I'm not saying this is the only way to think about punitive and assistive models. Like I could see compelling cases for other arguments, like caring about other outcomes. But the point is that you have to think carefully about this question. Like you have to think about what the consequences of your model are, and that can inform what kind of errors matter to you. So the final takeaway from kind of these 3 points, these 3 subtleties that I want to stress, is that we can't math our way out of thinking about fairness. Like these are human questions with ethical implications, and you need some human judgment to make an appropriate decision about how you define fairness in your context, and then how you go about measuring it. I think historically, there was a temptation when machine learning models first started being used to make these decisions to say, oh, models are just math and computers, so they can't be unfair. And at this point, that has been pretty thoroughly debunked. Like that's, I think, not a common opinion anymore. But there's a temptation to take the same logic, take the same reasoning, and just move it one step farther down the food chain. It's not, the models are math, so they must be fair. It's, I'm going to add a little bit of extra math on top of my model, and then it'll be fair. But you can't just rely on the math. You still need a human person applying human judgments to decide what makes your model fair. So these are kind of the subtleties of this question of how you should think about measuring the fairness of your model's output. Next, I'm going to talk about kind of an example case study experiment we did at Civis using some real-world data from one of our consulting engagements to show how these kind of subtleties and complications can manifest when you're doing this with real data that has like real complicated correlations and lots of complicated causal pathways within it. So to start off with, we're going to work with a data set from one of our consulting engagements. The features here are largely demographics and like socioeconomic type indicators. And the outcome is the probability that a person will sign up for the services of a state agency. And what we're going to look at is we're going to try to assess racial bias. So we're going to look at modeled outcomes for white people versus black people. And to do that, we're going to kind of make two fake worlds. So in one of these worlds, we're going to artificially balance ground truth. So remember, that was the first subtlety that you have to think about when you're doing this kind of exercise is ground truth balanced between the different classes that I care about? Here, we're making a hypothetical world where ground truth is totally balanced. And we do that by taking only the white people in the original data set and then randomly reassigning race labels. So at this point, race is totally uncorrelated with outcome. Our ground truth is totally balanced. That's one hypothetical world. The other hypothetical world is where we use the original imbalanced data set. So in the raw data, white people were dramatically more likely to sign up for the services of this agency. And so we use that as another hypothetical world where we're saying that's ground truth and ground truth is imbalanced. So that's our foundation, these two different worlds. Next, we're going to introduce known amounts of these different types of bias. So remember, subtlety number 2 was your data is not the truth. It's a biased representation of the truth. And there's two different ways it can be biased, or there's lots of ways, but in this case, we're talking about two different ways it can be biased. One of these is with sample bias. So in these two different worlds, we then sampled from the subpopulation differentially based on score thresholds and race assignments. So to introduce sample bias, we preferentially sampled white people with high scores and avoided or sampled at a lower rate white people with low scores, and then sampled black people uniformly. So this is injecting some known sample bias into these data sets that we're going to use to train some models. In a similar fashion, we injected some known label bias. So remember, our original labels are probabilities that you'll sign up for this agency's service. We converted those probabilities into binary labels, but used a different threshold for white people and for black people. So we used a low threshold for white people and a high threshold for black people. So using this, we can start with like different ground truths that we know, different hypothetical worlds, inject these different types of bias, train a model on the resulting data set, and then apply these different fairness metrics to the outcome to the predictions of those models to see how well these different metrics do in these different hypothetical worlds with different types of bias present in our training data. So that's the setup of the experiment. The two metrics that I'm going to talk about here are disparate impact and equal opportunity. Those are the ones I mentioned previously that are kind of generally popular in the literature and you hear people talk about. In the actual paper, we have a paper written up and posted on the archive. We address a couple other metrics. So if you're interested, I encourage you to go look up the paper on the archive. But we're applying these two metrics to those two hypothetical worlds and 4 different situations where we either have the no bias or we've introduced different types of bias. And this is what the results look like in the hypothetical world where ground truth is balanced. So on the left, we have the results for disparate impact. This is the ratio-based comparison. And on the right, we have the results for equal opportunity, which is the difference-based comparison. For disparate impact, because it's a ratio, values of 1 indicate no measured unfairness. And for equal opportunity, values of 0, because it's a difference, indicate no measured unfairness. So what you see here is, in this hypothetical world where ground truth is balanced between the classes, these metrics work pretty well. Like, they don't detect any bias, they don't measure bias in the case where we have not artificially introduced bias. But when we artificially introduce sample bias or label bias, they start detecting more bias. And then when we have both types of artificially injected bias in our training data set, the fairness metrics detect that as being even worse than either independently. So far, so good. When your ground truth is balanced, these metrics are performing fairly well. Unfortunately, the picture is dramatically less rosy if you're in a hypothetical world where ground truth is not balanced between your classes. So this is the same measurement, disparate impact over here on the left, equal opportunity. A value of 1 means no measured unfairness over here. A value of 0 means no measured unfairness over here. And we can see that in the unbalanced ground truth case, both of these metrics are measuring dramatic unfairness even when we haven't injected bias into our data. And even worse, it's even worse when you look at label bias in particular, because if you compare the case where we haven't injected any bias into our training data to the case where we've actually deliberately injected label bias, both of these metrics give you more or less the same result. And if you think about it, that kind of makes sense, because label bias is about labels being assigned differently between groups. But if ground truth is different legitimately between groups, you're already going to have differences in labels assigned between groups. So it's especially hard to detect this kind of bias. So, and here's a link to the white paper. Here I describe these two metrics. There are 4 more in the paper, and also a slightly more in-depth treatment of kind of the reasoning behind the experimental setup and this framing. So if you're interested, I encourage you to go check that out. So that's kind of the story. So what should we do about it? Well, there's not really a one-size-fits-all solution other than think hard about your inputs and outputs. Think hard about what's going into your model. Think hard about the process that generated your data. Think hard about the kind of the ground truth that you're trying to model in the first place, and how well your label, your dependent variable in your training data approximates the thing that you actually care about modeling. Think about what's going into your model, and think about what's coming out of your model. Think about where your predictions are going, what kind of effects, what kinds of consequences stem from the decisions made by this model that you have. These metrics that we talked about today can help. Along with other metrics, there's kind of quite a variety of different metrics people have proposed for measuring fairness, but you have to use them carefully. You have to think about these questions, these subtleties of what does fair actually mean in the context of the model that I'm building right here. If you do have good answers to those questions, there are also methods in the literature that will help you train models that automatically respect some of these metrics. So you can kind of include them in your objective function in some sense. But again, you really have to know, you really have to be certain that one of these metrics matches what fairness really means in the context of your problem, in what you're talking about. Use a diverse team to create these models and think about these questions. Throughout this talk, I've tried to emphasize that it's really a question of human judgment. But if everyone on your team thinks about things in exactly the same way, then you're not going to have good coverage on the kinds of issues, the kinds of things that you need to be thinking about when you're assessing these ethical questions of fairness. So, have a diverse team when you're doing this really human work of thinking about what fairness means in the context of your model. And then finally, just to repeat, think about your data, think about your predictions, think about the effects that everything has. I'll leave you with this quote from Cathy O'Neill's book, Weapons of Math Destruction, about how this is really a human moral question that your data is not the truth, and even if it were the truth, is it the kind of truth that you want to see in the world? Like that's a really human question, and we can't math our way out of having to use human judgment to answer it. Thank you.
Thank you very much. A really important and well delivered talk. Am I understanding correctly that there's another possible scenario where you have both label and sample bias, but they operate in opposite directions and can come out showing no bias at all?
Yeah, that could totally happen.
Oh man. All right, good talk. This is a really tough topic. Let's say you create a model that is unbiased when it comes to arresting between demographic. Right now it's biased because police officers choose different, like they sample differently. And let's say you deploy this model, and now now it's unbiased, it's great, but it's different from the real world now. Like the police officers would say, that's not how we work. We prefer doing this bias thing. Like, how do you square that?
Yeah, that's a good question, and it's a hard question. So I point to the end of Cathy O'Neill's quote, where sometimes it means putting fairness ahead of profit. Like, if just optimizing for like the performance metric of your model is the only objective function that you're considering, then I agree that this is hard to apply in that kind of case. I think the point I'm arguing for is that it shouldn't be the only thing in your objective function. Does that answer your question? Kind of?
Ethical question.
Yeah, it's an ethical question that I don't have like a hard and fast answer to. Okay. Be sure to let you all in time so we can get lunch.
Any more questions? All right. Thanks, Henry, again.